Hello everyone, my name is Shaun Levick from the Geospatial Ecology and Remote Sensing Lab. This is our environmental monitoring and modeling course, and today we're starting with Lab 6, Monitoring Vegetation Condition in Google Earth Engine. The objective of this tutorial is to develop the skills for assessing change in vegetation condition over time. How do we know if an ecosystem is stressed or is being disturbed? Quantifying changes and attributing causality can be challenging, particularly in ecosystems that have a large degree of intra-annual variability. One approach we have at our disposal is to compare attributes from recent years to those from a baseline period. In this lab, we will explore anomalies in vegetation condition, measured in terms of EVI or Enhanced Vegetation Index, to determine if condition greenness is increasing or decreasing over time. I'd like to start by acknowledging the Google Earth Engine team, the Geospatial Analysis Lab at the University of San Francisco, as well as the Server Mekong Consortium, who've put together some great tutorials and outlined some of the code that we're using today. Now, to get started, open up the code editor for Earth Engine. That's code.earthengine.google.com. And we're going to import the MODIS image collection mod 13A1. Remember that if you search for MODIS in the search bar, you will find a large number of products. So just add EVI to your search term, and here you will see different MODIS products, version 6 being the current latest. So we're going to choose the mod 11A1 006 Terra vegetation indices. If we click on that, we see that it's a 500 meter resolution product. Its cadence is every 16 days. It's a 16-day composite, and we have an NDVI and an EVI band. Note there's a scale factor, and also look at the min and max values. Okay, we're going to import that using the code. So we're just really defining it. So I'm going to copy out this piece here, paste it in over here. So we're creating a variable called collection, and that's going to equal our Earth Engine image collection, MODIS version 6, product mod 13A1, and importantly, we're just selecting that one band, EVI. Hit run, make sure that no errors pop up. Going back to our script, we're going to create a reference data set. So we want to understand the baseline conditions. MODIS data is available from 2000 onwards, so we're going to define our baseline period. It's from 2001 to 2010. So we're creating a variable called reference, and that's going to equal the collection up here, but we're going to apply a date filter from 2001 to the end of 2010, and we're going to sort that by system time start. System time start being a metadata property associated with the imagery that retains the date and time information for us. Again, we hit run just to make sure we have no errors in our script. And the next thing we're going to do is compute the mean EVI over the reference time frame. So what this is doing now is that for each pixel in that image collection, this will return the mean value. Importantly, note that we haven't defined any geographic bounds, so currently we're working with a data set for the entire globe. We can now display the mean using the code below. We're defining first some visualization parameters, variable viz. You'll need to vary these depending on where you are in the globe, and we're also applying a palette going from brown to yellow to green. And then to map EVI spatially, we're going to use map, add layer, mean, being the reference mean, applying the visualization parameters, and labeling our layer reference EVI. I'm going to copy that out and paste it in here. I'm going to hit run. And if everything works, we should see this layer reference EVI popping up. We can just check that it is coming up over here. And in no time at all, Google has queried that entire collection and returned the mean EVI value. Let's move over to Australia. And as that product loads, we are reminded what a dry continent Australia is. The mean is a bit unfair in very seasonal landscapes, and in some parts of Australia we have very long dry seasons, but this is a fair reflection of the mean condition. We can, however, adjust this metric if we want to. So just as an example, if we were interested in the maximum, I could just type max in here and hit run, and that would return the max EVI over the time period. You'd see then that we have a lot more green showing up in our higher rainfall portions. I'm just going to set that back to mean though, because that's what we want for our baseline condition. So moving back to our tutorial, navigate down, exploring trends against the baseline. We're going to create a new image collection for the period 2011 to 2018, and we're going to give this collection the name recent. So our code will create a collection of images that represent more recent conditions from 2011 to 2018. We'll calculate the recent mean, variable mean recent equals recent.mean, and we'll map that out spatially. So effectively we're doing exactly what we've done above, but just for a different time period. I'll hit run. That'll take a little while to load. Again, we're running this for the entire globe. Hovering over our layers tab, you can see the progress bars here. This shows that recent EVI is finished, and it's still calculating the reference EVI. Let's zoom in a bit to the top end of Australia, where our lab is located in Darwin. Remember that we can switch off the space map and rather use the satellite backdrop if we want. And here comes our EVI layers. So we turn those both off to start with. Let's bring up now the reference EVI, remembering that this is the mean value from 2000 to 2010. And then if we turn on the more recent EVI, this is the mean value from 2011 to 2018. It'll take a little while for that to populate. While it's doing that, we can also use the inspector tool to query a particular pixel, and that'll allow us to compare the values for the reference in recent data sets. I'm going to zoom in even closer now, bring up the Tiwi Islands. And the reason it takes a bit of time to load, just a reminder, we're still working with the data for the entire globe. Turn that one layer off. When I turn it back on, you can see some minor changes with it appearing a bit more green in the recent period. And you can notice that we have some greening up over here. If we take these layers off and zoom in a bit closer, we can see that this is actually a forestry plantation on the Tiwi Islands. Okay, so that's great, but how do we compare these more quantitatively, aside from just visualizing the spatial maps? Well, we can calculate and define anomalies, an anomaly meaning the departure from long-term average, by subtracting the reference mean from the more recent time series. So in our next bit of code, we're going to create a function to subtract the reference mean. Variable subtract mean is going to be a function that will return an image with the mean subtracted. And importantly, we're also going to copy properties. Remember, this command copies metadata properties of the image because we want to retain the system time start property. And then we'll create a variable called anomalies by mapping the subtracted mean over the recent time series. Variable anomalies equals recent.map subtract mean. Copy that. Paste it here. Run. And just a reminder that what we're doing now is effectively subtracting the mean of the reference time period from each individual image in the recent time period. To visualize this spatially, we'll use map add layer. And I'll just zoom out a bit. And now you'll see we have the cumulative anomaly popping up here. The reason why it's a cumulative is because we've summed it. So we've added the anomalies on each image in the recent time series. So I'm going to turn off these other two layers and just look at the anomaly map when it loads. And here it comes through. So what this shows areas, if you look at our palette here, going from dark red through yellow to dark green. So the dark red areas are where we have a negative anomaly, where EVI has been decreasing over time. And in dark green, we have a positive anomaly, where EVI has increased over time. We can take this a step further by charting these values over time in a graph. So what we'll do is calculate the cumulative EVI for a specific area using the iterate function, and then graph the cumulative anomaly over time. We're going to start by creating a timestamp for the most recent image in the reference collection, making that time 0. We'll paste that in here. And then the next thing we're going to do is create a list that contains a single image of zeros with a time of time 0. We need to rename this list to EVI to match the other images in the series. Effectively, this is just a holder. This is a empty image of zeros where we can map the EVI anomaly into. Now we're going to paste the following code into the code editor to iterate through time, and you see we accumulating, so we adding the anomalies from each subsequent image. We're going to create a vector geometry and call it ROI, and then plot a chart using these next two bits of code. So just to recap these three steps here of getting the time step, creating the empty list, and then the function to iterate through, this is really just a way of structuring the data so that we're able to plot out that chart. I'm going to create a little ROI over here on the Tiwi Islands. So just a little vector geometry, rename that ROI, and then I'm going to come down and insert the charting parameters. So first we're going to define our chart parameters. What I mean by that is we're just defining a variable called chart param with a title, cumulative EVI anomaly over time, H-axis title, and vertical axis title. And then the actual chart is this piece of code here. To plot the chart, we define a variable and use this function. So we want to use chart image series by region. And importantly, we need to define the collection, which is cumulative, this one up here. And we need to define the region, ROI, that's the geometry we've defined. And we need to decide how to reduce within that area. We're just going to take the mean. We need to specify the band that we're using and the scale of the imagery. So copy that, paste it in here, and run. And you'll see the console tab light up. Cumulative is not defined in this scope. That means I forgot to define it. Let's just have a quick look. I forgot to insert this piece of code, so we'll copy that and bring that in before the chart parameters over here. We need to run the iteration. Hit run now, and you'll see that our chart is working. So whenever you find an error here where something's not defined, just check that you haven't missed one of these little snippets. Okay. Now we're asking quite a lot of Earth Engine here, but it doesn't take long to actually plot that out. And here we have our cumulative EVI anomaly for this block over here. And what we see is that the anomaly is 0 for the period of 2001 to 2010, because that was our reference period. So we would expect the anomaly to be 0 there. But then in a more recent time period, you can see that we still have that seasonal change, that seasonal cycle in EVI, but this shows how it is accumulating over time. However, if we bring that block to one of these darker brown areas, like here, for example, and I hit run now, we'll likely see that EVI is decreased over time. But the interesting thing about plotting the chart is that you can see the pattern of change. You can see whether it's a consistent increase and decrease over time, or if there's something abrupt happening. So you might get a rapid change and then not much changing for the next few years. So here we can see, quite interestingly, that at first there's a positive anomaly for a couple of years, and then we have that negative anomaly over time. Okay, so this gives you a nice tool for exploring, in this case particularly EVI anomalies in space and time. But now that you have this code, remember to save it. You can apply this in a number of different situations. And the exercise I have for you today is to think about how you can adapt this approach to other types of data, such as land surface temperature or rainfall, for example. So I hope you found that useful. That's the end of Lab 6 in Environmental Monitoring and Modeling. I'm Shaun Levick from the Geospatial, Ecology and Remote Sensing Lab. Thanks for your time. See you next week in Lab 7. Cheers.